Welcome to The Explainer. Today, we're diving into something truly fascinating, a breakthrough in AI that's not about building bigger machines, but about thinking differently. It's a story of how a bit of 19th century geometry is solving one of today's biggest tech problems and shrinking massive AI models by an incredible 96%. So let's just kick things off with a number, 3 terabytes. That's 3 terabytes of RAM. That's what you need to power a modern semantic search engine for about 1 billion documents. I mean, it's a colossal amount of hardware, the kind of thing that puts this tech way out of reach for almost everyone, except the giants. And this is the question that sparks a really brilliant breakthrough. See, the solution isn't about just throwing more raw computing power at the problem. It's about a fundamental shift in perspective. So let's dig into what that actually means, and we've got to start with the problem itself. Okay, so the terabyte problem, you know. Every single time you type something into a search bar, there's an AI working behind the scenes. Its job is to turn your words into this long list of numbers. It's called a vector that somehow captures the meaning of what you said. It's how machines understand language. But as we're about to see, this comes at a pretty staggering cost. And we're not talking about a short list of numbers here. The industry standard is a vector with 768 different numbers, and that's for every single piece of text. So, as you can probably imagine, that creates just a massive data footprint for every document the AI has to deal with. And this is where things get kind of wild, because this problem just explodes when you try to scale it. 1 million documents, sure, that's manageable, 3 gigs of RAM, but 1 billion documents? Whoa. You are suddenly staring down the barrel of 3 terabytes of RAM and a cloud bill that's tens of thousands of dollars every single month. This is, a problem that only big tech can really afford to solve. All right, so A squared peg, a round hole. Here's the crucial insight, the big aha moment. What if the problem isn't actually the size of the data? What if it's the shape of the mathematical box we've been trying to cram it into this whole time? And this slide just lays it out perfectly. It is a fundamental mismatch. Language, when you think about it, is structured like a tree, right? It's hierarchical. Concepts branch out. Animal splits into mammal and reptile. Mammal splits into dog and cat. It grows exponentially. But for years, we've been forcing this tree structure into a flat, grid-like space called Euclidean space. It is literally like trying to organize an entire library by just throwing every single book onto one giant flat floor. It's a total mess. And to stop all the concepts, all the branches of our language tree from just crashing into each other on this flat floor, we've had to resort to brute force. We just keep making the floor bigger and bigger by adding hundreds and hundreds of dimensions. So, the right-shaped space. This begs a question, right? What if we just used a space that was already shaped like a tree? And this is where a really old, kind of beautiful idea from geometry gives us a surprisingly elegant solution. Now, this isn't some brand new cutting-edge discovery. We are talking about a type of geometry from the 19th century. It just so happens to be the absolute perfect container for the structure of language. It's called hyperbolic space, and in this world, the space itself expands exponentially, just like language does. A really great way to visualize this is something called the Poincare desk. So picture a circle. Right at the very center, you have the most general concepts, like animal. But as you move out from the center toward the edge, the amount of available space just expands infinitely. This gives you more and more room for all the specific concepts: dog, cat, poodle, Siamese, and they can all exist without ever bumping into each other. The best analogy is having a Christmas tree box that's already shaped like a Christmas tree inside. You're not smashing the data down to fit. You're putting it into a container that has the perfect shape from the start. The geometry itself does all the heavy lifting for you. Okay, so how the bending works. This is the really cool part. How do we actually take our normal flat vectors and project them into this new curved space? Well, it's a pretty clever 3-step process. So first, a standard AI model does its thing and generates that big old 768-dimension vector, business as usual. Then, step 2, a neural network acts as a kind of summarizer, and it shrinks that vector way down to just 32 dimensions. And then, here's the magic trick. A mathematical function called an exponential map takes that little 32D vector and literally bends it into the curved hyperbolic space. So how does the model learn to do all this without just scrambling everything? Well, it's basically trained to balance 2 goals, and they're equally important. First, it tries its best to keep the relative distances between concepts proportional to how they were in the original space. But second, and this is absolutely key, it makes sure the order of what's most similar stays exactly the same. And that is the secret sauce. Because for search, knowing what is closest is way more important than knowing the exact distance. You don't really care if puppy is 0.1 units away from dog. You just care that it's the #1 closest result, and definitely closer than, say, car. Preserving that ranking turned out to be the key to keeping the quality high. So this stunning payoff. The theory is elegant, it's beautiful, but does it actually work in the real world? Let's look at the numbers and see how this geometric approach actually stacks up against the massive industry-standard models. Honestly, the results are just remarkable. Look at this, the tiny 32-dimension hyperbolic model, CGT32. It gets a quality score of 0.812. That is almost identical to models that are 12 or even 24 times larger. It's incredible. And this visual just drives the point home, doesn't it? The difference in size is just dramatic. It really highlights the absolutely incredible efficiency gain you get going from 768 dimensions all the way down to 32. Let's put a number on it. That's a 24-fold reduction in size. In exchange, you get about a 2% dip in quality, which means you're getting a 96% gain in efficiency. That is an amazing trade-off. And this isn't just some theory. This is a real game changer. It means we can have powerful AI-driven search running completely offline on our phones. It means startups can suddenly afford to access big tech-level capabilities. It means we can embed AI directly into all kinds of Internet of Things devices. It really democratizes the whole field. And that really brings us to the core takeaway. For decades, we've been using brute force computation, just throwing more servers and more power at this thing to solve what was never a computation problem to begin with. It was a geometry problem all along. And that leaves us with this final thought. The holy grail of vector search wasn't a bigger model. It was a smaller space. A space that was just curved in exactly the right way. And maybe the biggest breakthroughs in our future won't come from making our tools bigger, but from finally choosing the right tool and the right shape for the job.